In section 6.7, we'll be continuing to discuss integration with substitution. Let's first think about integrating involving inverse trig functions. So this might actually be misleading. We're not actually integrating inverse trig functions. That's something you would learn how to do in BC Calc. But what we're doing is integrating something that results in an inverse trig function. And so remember that the derivative of arc sine of x was 1 over square root of 1 minus x squared. And so that's where we get this formula from. If I take the antiderivative of 1 over square root of 1 minus x squared, I would get arc sine x. Same idea with the integral of dx over 1 plus x squared. That gives me arc tan x plus c. Now the one that's missing is arc cosine x. That would just be negative dx over square root of 1 minus x squared. But we can rewrite that as just negative arc sine x. With this first one, we can factor out that -1 coefficient. And it would essentially be the same answer. The constant might just change there. So we usually just stick with this format for arc sine, arc tan. Now there is a special form for U substitution. Oftentimes this is not just going to be a 1 or an x squared in either of those forms. And so if we're integrating square root 1 over square root of a squared minus u squared, that will give me arc sine of u over a plus a constant. And if we're integrating 1 over a squared plus u squared, we get 1 over a arc tan of u over a plus c. That comes from factoring things out. Like if I think about plugging in u over a squared and then factoring in a squared out there, that's where that's coming from. Don't stress about it too much, but you do have to remember this little 1 over a for arc tan. It will be important that you remember that part. So first of all, in number 1a, we see the integral of dx over square root of 4 minus x squared. When you see something like this where there's just like some x squareds in the denominator with a constant, square root or not, you might just start thinking inverse trig functions. Notice there is no variable in the numerator there. That's a good indication that this might be inverse trig. So this looks like the first form we have, dx over square root of 1 minus x squared, but that's not just a 1. So it looks like arc sine, but I'm going to have to do a little bit more work. That's going to tell me I need to do my U substitution form. So here I would notice I see that my a squared is 4. That's this part right here. So that means my a is 2. And my u squared is x squared. So my u is just x. Now you do have to make sure that your du is present. So the derivative of u is just dx. I see that here in my integral, so I'm good to go. If this is just an x, I don't have to worry about the normal U substitution technique. I just use this U substitution form. And so I can go ahead and say that this is going to be arc sine of u over 2, but my u is x, my a is 2, and then don't forget your plus c. Sometimes you're going to have something a little bit more complicated. So like in part B, it's the integral of dx over 2 plus 9x squared. I recognize that that is the format of the arctan form. And so we're just going to identify our a and our u like we did before. So our a squared is 2. That means our a is square root of 2. Our u squared is 9x squared. And so that means u is 3x. So making sure you're taking the square root of the 9 and the x there to get u equals 3x. So my derivative is 3 dx. Now what you'll notice is I just have a plain old dx here. I don't have the 3 dx, so I will have to do that dividing by 3. So it might help you to rewrite your integral as 1/3 the integral of du over square root of 2 squared plus 3x squared. This kind of gets you in that format that we're talking about here, du over a squared plus u squared. The 1/3 again comes from balancing that du. So make sure that you do have that du present. When I take my antiderivative, the 1/3 comes along for the ride. Then in my formula, I have 1 over a. My a was square root of 2, so I have to multiply by 1 over square root of 2. Then arctan of u over x. So u is 3x, sorry, u over a, and a was square root of 2 plus a constant. You can simplify this a little bit just by saying 1 over 3 square root of 2, but otherwise there's not anything you can really do to simplify, so that will just be our answer. Let's also talk about the change of variable method. This is a harder method to spot. When I look at an integral such as x times square root of 2x minus 1, you might be thinking, oh, this seems like a normal U substitution problem. I make U the part underneath the radical. The difference is I notice that the degree of the part underneath the radical is the same as the degree outside the radical. When I notice that happening, I'm probably going to use this method. So in example A, it's that integral we were just talking about, the integral of x times square root of 2x minus 1 dx. So let's start out the way we normally would. U equals 2x minus 1. My du is 2 dx. I don't see my 2 there, so I'm going to have to divide. That feels pretty normal. But the problem is we have this extra x outside, and when we make our U substitution, we have to make sure that we don't have any x's left. We just have constants and u's and du's. So what we're going to have to do is rewrite my u equation to solve for x. So this would give me u plus 1 is equal to 2x, and u plus 1 over 2 is equal to x. That way I can substitute in for that x, but it will be in terms of u. So my integral will be, so I have my 1/2 out in front. That comes from my du. The integral, my x is now u plus 1 over 2. And then times square root of u, or u to the 1/2 du. And then what I'm going to do is distribute this through. I still can't integrate it this way. I'm going to take this 1/2 from the u plus 1. I'm going to factor it out in front, so that's going to be 1/4. And then I'm distributing u plus 1 times u to the 1/2. So u times u to the 1/2 would be u to the 3/2. I add those exponents there. Remember, this is u to the first plus u to the 1/2 du. Now this is a normal power rule type of problem. And so I can go ahead, know what's happening. I can go ahead and integrate that. So I have 1/4 times u to the 5/2 times 2/5 multiplied by the reciprocal plus u to the 3/2 times 2/3. Plus c. I do want to make sure to replace that u. I'm not going to worry about distributing this 1/4 or anything. You absolutely can if you want to. But the last thing is to just replace that u. My u was 2x minus 1. And in this case, it's actually okay if your plus c is either inside the parentheses with the 1/4 or outside. Either one is going to work for you. All right. In part B, again, this looks similar to what we talked about before. It looks like a U substitution problem. However, the degree doesn't seem to be matching up. And so I still will make my u the part that's underneath the radical. So it looks like my u is going to be x plus 4. The derivative of that is just dx, which is easy. That's there. And then I need to solve my u for x so that I can replace that x from the numerator. So my x is just u minus 4. Solving this equation for x, getting the x by itself. So then when I rewrite my integral, I'm going to rewrite this with the radical in the numerator instead. Remember, this would be x to the negative 1/2, or x plus 4 to the negative 1/2 in the numerator. So what I have is, for 2x plus 1, I would have 2 times my x, u minus 4, plus 1, times my x plus 4 to the negative 1/2, but that's just a u, du. If I simplify that a little bit, that's just 2u minus 7, so this would be 2u minus 8 plus 1 times u to the negative 1/2 du, and then we can distribute there. So I'd have 2u to the 1/2 minus 7u to the negative 1/2 du. Take my antiderivative. So I'd have 2 times u to the 3/2 multiplied by 2/3 minus 7 times u to the positive 1/2 multiplied by 2 over 1 plus c. And then I need to plug my u back in. So I have 4/3. My u is x plus 4. I'm looking back up here for my u. Minus 14, x plus 4 to the 1/2 plus c.